In this lecture, we are going to discuss about universal logic gates. We have two universal logic gates, NAND gate and NOR gate. So specifically in this lecture, we are going to have discussion on logic gate designing using only NAND gates. So we know that total we have 7 logic gates: AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gate. So this is the summary of logic gate symbols. Symbol of AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gate. And this is a summary of truth table of all the logic gates. So we have drawn here a common truth table with the two common inputs A and B with the four combinations as 0 0, 0 1, 1 0 and 1 1. So here we have written the output of AND gate as B. You can see here. This is the output of NAND gate Q. We can see here. This is the output of OR gate, that is R, we can see here. And this is the output of NOR gate, that is S, we can see here. And this is the output of XOR gate, that is T, we can see here. And this is the output of XNOR gate, that is U, we can see here. And the NOT gate truth table, that is not shown because that is working on a single input A. If A is 0, V is 1, and if A is 1, V will be 0. So how we define a universal logic gate? A universal logic gate is a logic gate which stand alone or in a group can implement any Boolean function, any complex Boolean function, any big Boolean function without using any other logic gate. So with the help of universal logic gate, we can construct the other logic gates. So we have two universal logic gates, NAND gate and NOR gate. So with the help of these two universal logic gates, we can design any other logic gate. And why they are most widely used and called as universal? Because they are economical and easier to fabricate. So quick review about NAND gate. This is the logical symbol of NAND gate. A and B are inputs and Q is output. And how Q is related to A and B? Q is equal to one input dot another input to the whole complement. One input is A, second input is B. So what we are doing is one input dot another input to the whole complement. And this is the truth table of NAND gate. We have shown here the four combinations of A and B as inputs that can be 0 0, 0 1, 1 0 or 1 1. And Q is the output of NAND gate. For 0 0 combination output is 1. For 0 1 combination it is again 1. For 1 0 combination also it is 1, and for 1 1 combination it is 0. So what is the conclusion here? That if any of the input is 0 or all the inputs are 0, then output is 1. For example, here B is 0, output is 1. Here A is 0, output is 1. Here both A and B are 0, so output is again 1. So now we are going to design all the 6 logic gates by using only NAND gate. So first designing is NAND gate as an inverter. So we know that in the NAND gate 2 inputs minimum are required, that is A and B. But for the inverter, that is the exceptional case, that is working on a single input. So how we convert this NAND gate to the inverter? By short circuiting both the inputs and drive here with a common input terminal A. So that means this common input signal is passed to both the inputs here. So usually we have the expression of NAND gate as A dot B to the complement. So here A is A and the B is also A. So what we can write this Boolean expression as output of this NAND gate, that is V we are taking as output of inverter, and that is equal to, in general expression is A dot B to the complement, and for this particular logic circuit A is going to remain A and the B is also A. So we can write this expression as A dot A to the whole complement, and A dot A in the digital electronics we know this is A. As per the AND law, A dot A is A. So we write it as A and this becomes A complement, and A complement is the Boolean expression of inverter. So we have verified that this particular circuit is acting as an inverter that we have constructed using only NAND gate. Then second we have AND gate designing using only NAND gate. So here we have taken one NAND gate. We provide the input here A and B. So what is the Boolean expression of this NAND gate? That is A dot B to the complement. And for finding the output as an AND gate, we add one more NAND gate, and this NAND gate is acting as an inverter. In the last slide we have seen that if we want to go for inverter, we short circuit both the inputs and drive here a common input signal. So this signal we want to complement, because if we take complement to the complement, that will get cancelled out, and expression we will get here is A dot B, and that is the expression of AND gate. So what we are doing is we are inverting this signal by putting one inverter using only NAND gate. So when we are putting one inverter using NAND gate, so that is inverting this signal. So when we invert this signal, so we get complement to the complement, and that will get cancelled out, and the expression we get here A dot B, and output variable we are taking here is P. P is the output of AND gate we are taking, and the Boolean expression we are getting is AND gate expression, that is A dot B. So we have verified that this particular circuit is acting as an AND gate, and that we have drawn using only NAND gates. Then next we have OR gate designing using only NAND gate. So here we have taken the two NAND gates acting as inverters. So this is the NAND gate acting as inverter, that is working on input signal A. So that is complementing signal A. So at the output we get A complement. This is the another NAND gate acting as an inverter, that is taking the signal B, and that is complementing signal B. So here we get B complement. So here we have A complement, here we have B complement. So these two inputs we are passing to the another NAND gate. So what this NAND gate is doing, that is taking one input dot another input to the whole complement. So here we get one input, that is A complement, dot another input, that is B complement, to the whole complement, and this is of form complement of product. And as per the De Morgan's theorem, we can write it as complement of product is equal to sum of individual complements. So we have here A complement to the complement plus B complement to the complement, and complement to the complement gets cancelled out. Here we get A and here we get B. So final expression we get here A plus B, and that is the Boolean expression of OR gate. So in this way we have verified that this particular designed circuit is acting as an OR gate, and that we have designed using only NAND gates. Then next we have NAND gate acting as NOR gate, and already we have designed the OR gate using only NAND gate. So this is the circuit we have designed for the OR gate. In the last slide we have seen with the help of these three NAND gates we can design OR gate. So for the NOR gate, what we are doing is we are inverting the output of OR gate. This is the output of OR gate. So how we can invert this? By putting one more NAND gate acting as an inverter. So this inverter is complementing this. So finally we get here A plus B to the whole complement, and that is the expression of NOR gate. and the output variable we are taking for the NOR gate acting as NAND gate, NAND gate acting as NOR gate as S. Then we have next designing, that is NAND gate as XOR gate. So here we have taken one NAND gate with the two inputs A and B. We get here output A dot B to the complement. So this signal we are passing to two more NAND gates. Here we are passing this signal and the another input is A, and here we are passing this signal and the another input is B. So what this NAND gate is doing, that is taking one input dot another input to the whole complement, that is A dot B to the complement to the whole complement. And what this NAND gate is doing, that is taking one input B dot another input, that is A dot B to the complement to the whole complement. So how we can solve this expression? This is of the form complement of product, that is equal to sum of individual complements. So this becomes A complement plus A dot B to the complement to the complement, and complement to the complement will get cancelled out. Here we get AB. So here we have the expression A complement plus AB. And when we solve it, this is complement of product, that is equal to sum of individual complements. So here we get B complement plus AB to the double complement. Double complement will get cancelled out. Here we get B complement plus AB. Here we get A complement plus AB. Here we get B complement plus AB. And these two are the inputs to this NAND gate. So what this NAND gate is doing, that is taking one input, that is A complement plus AB dot another input, that is B complement plus AB to the whole complement. So when we solve this expression under complement, so we multiply A complement with B complement, we get here A complement B complement. Then we multiply A complement with AB, so A complement and A result will be 0. So when we multiply AB and B complement, B complement will be 0. And when we multiply AB with AB in the digital electronics, if same variables are multiplied, they will remain single time that variable. So AB dot AB will be AB. So here we get A complement B complement plus AB to the whole complement. So here how to solve it further? Again apply the De Morgan's theorem. Complement of sum is equal to product of individual complements. So here we have A complement B complement to the whole complement dot AB to the complement. So how to solve it further? Again apply De Morgan's theorem. Complement of product is equal to sum of individual complements, and here also complement of product, that is equal to sum of individual complements. Here we get A plus B, here we get A complement plus B complement. Now solve it further. A is multiplied by A complement, that leads to 0. Then A is multiplied with B complement, we get it here. Then B is multiplied with A complement, we get it here. And B complement is also 0. So final result we are getting here is AB complement plus A complement B, and that is the Boolean expression of XOR gate, and the output variable we are taking is T. So T is the output of XOR gate, and this particular circuit we have designed using only 4 NAND gates. So this is a very important question, that design the XOR gate using only 4 NAND gates. So if we can design the XOR gate using NAND gate, so designing XNOR gate is very simple. These 4 NAND gates we have utilized for the construction of XOR gate. So now we have to invert the output of XOR gate so that it works as an XNOR gate. So what we are doing is we are putting one more NAND gate, and this NAND gate is acting as inverter. So here we have expression A complement B complement plus AB to the whole complement, and this particular inverter is complementing this. So here we have complement to the complement, that will get cancelled out, and final expression we get here A complement B complement plus AB, and the output variable we are taking for the XNOR gate as U. So we have verified that we get the expression of XNOR gate here using this circuit. So this circuit is acting as XNOR gate, and that we have designed using only NAND gates. These are the references I have used. Thank you.